Hey everyone, ready for another deep dive? Today we're going to tackle something that's all around us, literally.
It's true. We use them for energy, in plastics, even in medicines.
You got it. We're diving into the world of hydrocarbons.
Sounds exciting.
It is. But don't worry, no PhD in chemistry required. We'll break it down nice and easy.
We'll explore what they are, the different types, and how they react to form, well, pretty much everything.
Okay, so first things first. What are hydrocarbons? Like, what makes a molecule a hydrocarbon?
Well, the name kind of gives it away. They're compounds made up of just two elements, carbon and hydrogen.
Right. Hydro for hydrogen, carbon for, well, carbon. Simple enough, right?
You'd think so? But even though their building blocks are simple, hydrocarbons come in a huge variety of forms.
I bet. Just thinking about fuels, we've got natural gas, gasoline, diesel.
All hydrocarbons, right?
Exactly. And then there's all the plastics, waxes, even some solvents. It's mind-boggling how many different compounds we can make with just carbon and hydrogen. So how do we make sense of all that variety? Is there some kind of system, like categories or families of hydrocarbons?
There is. We broadly classify them into three main groups: saturated, unsaturated, and aromatic.
Okay, three main branches on the hydrocarbon family tree. What distinguishes each group?
It all comes down to the types of bonds between the carbon atoms. Saturated hydrocarbons, like alkanes, have only single bonds.
Single bonds, got it. Like each carbon is holding hands with its neighbors, just one hand each.
Exactly. Now, unsaturated hydrocarbons have at least one double or triple bond between carbons.
Ah, so they're holding hands and linking arms.
Yeah.
And that makes them more, I don't know, excitable.
You could say that. Those double and triple bonds make them more reactive. Alkanes have double bonds. Alkenes have triple bonds.
Okay, single bonds are chill, double and triple bonds are ready to party. What about those aromatic hydrocarbons? Those sound kind of fancy.
They're a bit special. They have ring structures with electrons that are, well, delocalized, spread out over the whole ring.
Like a molecular dance party. Benzene, right. That's the classic six-membered ring.
That's the one. And because of that delocalization, aromatic hydrocarbons have unique stability and reactivity.
Okay, I'm starting to see how those tiny bonds make a huge difference.
No.
Let's focus on the simplest ones first. Those chill, single-bonded alkenes.
All right, alkanes it is. They're chains of carbon atoms linked by single bonds, with all the other bonds filled in with hydrogens.
And they're saturated because they have the max number of hydrogens, right? No more room at the end.
Exactly, like a sponge that's soaked up all the water it can hold.
Okay, so they're full of hydrogens, and they're pretty stable, I'm guessing.
Very stable. And guess what? A lot of the hydrocarbons in fuels, things like gasoline and diesel, are alkenes.
Whoa, so those little guys are powering our cars and planes. Amazing.
They are. But of course, burning fossil fuels has an environmental impact, something to keep in mind.
Right, gotta think about those emissions. But for now, those alkenes are keeping our world running. What else are they used for, besides fuels?
Oh, all sorts of things. Natural gas for heating and cooking is mostly methane, the simplest alkane. And waxes, like in candles, are also alkanes.
Wax. Never thought about that.
Yeah.
Okay, so even though they're simple with just single bonds, alkenes are pretty darn versatile.
They are. And even the simplest one, methane, is pretty fascinating when you look at its three-dimensional structure.
Methane, the one that comes from cows and, well, you know. It can't be that complicated, can it? Just one carbon, four hydrogens.
It's simple, yeah, but it actually forms a 3D shape called a tetrahedron.
A tetrahedron. Sounds fancy. What's that look like?
Think of a pyramid, but with a triangular base. The carbon sits in the middle, and the four hydrogens are at the corners.
Ah, okay.
Yeah.
So even though we draw it flat on paper,
Yeah.
it's actually a 3D pyramid.
Precisely. And as we add more carbons to make longer alkanes, those chains can twist and turn in space.
So they're not just straight sticks, they're more like wiggly worms.
Exactly. And those different shapes, those conformations, can actually influence the molecule's properties, even if it has the same formula.
Okay, so same atoms, different arrangement, different properties. Got it. What about isomers? Are those like alkanes that play musical chairs with their atoms?
You got it. Isomers are molecules with the same molecular formula, but different structural arrangements.
Like building a house.
Yeah.
You can use the same bricks and wood, but arrange them differently to get totally different houses.
Perfect analogy. And isomerism explains why we have so many different organic compounds, even with just a few elements.
It's like a molecular Lego set. So many possibilities. But how do we keep track of all these isomers? There must be a million ways to arrange those atoms.
There are. Luckily, we have a systematic naming system called IUPAC nomenclature. It's like a code that tells us everything about a molecule's structure just by looking at its name.
IUPAC nomenclature, the decoder ring for organic chemistry.
Yeah.
Sounds complicated.
It can be, but it's essential. Let's start with the basics. The first four alkanes have common names: methane, ethane, propane, and butane.
Ah, those I remember. But I bet things get more complex with longer chains.
They do. For alkanes with 5 or more carbons, we use prefixes from Greek numbers, so pentane for 5, hexane for 6, and so on.
Pentane, hexane. It's like learning a new language.
It is, in a way. And then we add prefixes and numbers to indicate any substituents, which are groups attached to the main chain that aren't just hydrogens.
Substituents, like side branches on the main chain. So if we have a butane with a methyl group on the second carbon, we'd call it 2-methylbutane.
Exactly. The 2 tells us where that methyl group is located.
Okay, I'm starting to get the hang of this molecular naming game. But where do these alkenes come from in the first place? Are they just found in nature, or can we make them?
Both. We find them abundantly in fossil fuels like petroleum and natural gas, but we can also synthesize them in the lab.
Synthesize them, so we can actually build these molecules from scratch.
We can. There are a few different methods, like hydrogenation, where we add hydrogen to alkenes or alkanes to convert those double or triple bonds to single bonds.
So we're basically saturating them with hydrogen, turning them into alkanes.
Exactly. Another method is decarboxylation, where we remove a carbon dioxide molecule from a carboxylic acid.
Decarboxylation. Sounds a bit like decaf, but for carbon.
Haha, I like that. But yeah, we're essentially snipping off a carbon dioxide molecule to shorten the chain and make an alkane.
Okay, so we've got options for making these alkanes. Now let's talk about what makes them unique. What are their personalities like?
Well, one key thing is that they're nonpolar.
Nonpolar, so no positive or negative ends. Kind of neutral, like Switzerland.
Right. And because of that, they're generally pretty inert, meaning they don't react easily with other stuff.
So they're the introverts of
Yeah.
the hydrocarbon world. Content to just chill.
Pretty much. But there are ways to get them to react, especially with a bit of heat, light, or a catalyst.
So we can coax them out of their shell. What kind of reactions are they willing to do?
One big one is combustion.
Combustion, like burning.
Yeah.
So that's why they're such good fuels.
Exactly. Burning alkanes releases a ton of energy, which we use to power everything from cars to power plants.
Wow, those alkanes are the unsung heroes of the modern world.
They are, but of course, combustion also produces byproducts, mainly carbon dioxide and water.
Right, those emissions are something to be mindful of. What about other reactions? Can alkanes do anything besides burn?
They can. One is halogenation, where we replace a hydrogen with a halogen, like chlorine or bromine.
Ah, adding those halogens. And those halogenated alkanes, they're used for all sorts of stuff, right?
They are solvents, refrigerants, even in making plastics.
Okay, so we can tweak those alkanes to make them even more versatile. What else?
There's also isomerization, which rearranges the carbons in the chain to make a different isomer.
Isomerization, those molecular makeovers. So we can transform one alkane into another just by rearranging the atoms.
You got it. And this is actually used in the petroleum industry to improve the quality of gasoline.
Wow, so we're manipulating those alkanes at a molecular level to make better fuels.
It's all about understanding those structural differences and how they impact a molecule's behavior.
This is incredible. It's way more complex than I imagined. But I'm ready to move on to those more excitable hydrocarbons, the alkenes with their double bonds.
Let's do it. Things are about to get a lot more reactive, ready to explore the world of alkenes. Those triple bonds are waiting.
Bring it on.
Yeah.
I'm curious to see how those triple bonds make them even more reactive than alkenes.
Well, for starters, alkenes have at least one carbon triple bond, making them even more unsaturated than alkenes.
Okay, more unsaturated meaning they're even more eager to react, right?
Exactly. They're like the daredevils of the hydrocarbon family, always looking for a reaction.
Haha, I like that. But before we get into those reactions, can you break down the structure of a triple bond for me?
Sure. Imagine 2 carbon atoms, right? They're holding hands with one hand, that's the sigma bond, just like in alkanes and alkenes.
Got it, one sigma bond. So what about the other 2 bonds in the triple bond?
Well, those are pi bonds. It's like they're linking arms with their other 2 arms, but those linked arms, those pi bonds, are weaker than the handhold.
Ah, I see. So one strong sigma bond and 2 weaker pi bonds. That definitely sounds like a recipe for reactivity.
It is. And those triple bonds also impact the shape of the molecule.
How so? Do they make the molecule bend in weird ways?
Not exactly. Alkenes actually have a linear geometry around the triple bond. So the part of the molecule with the triple bond is a straight line.
Straight line, huh? So no kinks or curves, like a molecular highway?
Yeah.
And that means no cis and trans isomers for alkenes, right?
You got it. With that linear geometry, there's only one way to arrange the atoms around that triple bond.
Well, that does simplify things a bit. No need to worry about those geometric isomers this time.
Exactly.
Okay, so let's move on to naming these alkenes. Is it similar to alkenes, just with 8 instead of 8ing?
You're a natural at this. That's exactly right. We find the longest chain containing that triple bond, number starting from the end closest to the triple bond, and use the sine suffix.
Okay, so 2 carbons with a triple bond would be at the end, right?
Exactly. And ethene actually has a common name you might recognize, acetylene.
Acetylene. Isn't that used in welding torches?
You bet. Those torches get so hot because when acetylene burns with oxygen, the flame can reach over 3,000 degrees Celsius.
Whoa. That's hot enough to melt steel? I definitely wouldn't want to mess with an acetylene torch.
Definitely a job for professionals.
Okay, so the acetylene for welding. What else are alkynes used for?
You might be surprised to learn they're used as starting materials for a lot of things, including plastics and even perfumes.
Wait, perfumes? Those delicate scents coming from a molecule with a powerful triple bond? That's kind of wild.
It is. But remember, we can use chemical reactions to transform those triple bonds into other functional groups, which contribute to the overall scent of a perfume.
Ah, so it's like we're using alkynes as building blocks to create these amazing fragrances.
Exactly. That's the beauty of organic chemistry. The possibilities are endless.
Okay, enough of the perfume. I'm ready to hear about those reactions. Those triple bonds must be itching to react, right?
Oh, absolutely. Alkynes, just like alkenes, are big fans of addition reactions.
Addition reactions where we break open those pi bonds and add stuff across the triple bond.
Got it. Right. But remember, since alkanes have 2 pi bonds, they can actually add 2 molecules of a region.
2 molecules. Wow, so we can really pack those alkynes full of new atoms.
Exactly. And we can use this to our advantage. For example, we can add hydrogen to completely saturate the triple bond, converting it all the way to an alkane.
So we're going from triple bond to double bond to single bond just by adding hydrogen.
Precisely. We can also do a partial hydrogenation, stopping at the alkene stage.
So hydrogenation gives us options depending on how much hydrogen we use. What about halogens? Can we add those to alkynes too?
Of course. Alkenes react readily with halogens like chlorine or bromine.
And I bet those halogens love to add across those triple bonds.
You bet. And they add twice, forming tetrahalocanes.
Tetrahaloalkanes. So we end up with 4 halogen atoms attached. It's like a halogen party on that alkyne.
Haha, that's one way to put it.
Okay, so we can hydrogenate alkynes, we can halogenate them. What other fun reactions can we do?
Well, remember when we talked about adding water to alkenes to make alcohols?
Yeah, I remember that. Does the same thing happen with alkenes?
Sort of. When we add water to an alkane, we actually get a ketone.
Like ketone. We've talked about those before. So we can make ketones from alkenes and alkenes?
Exactly. Different starting materials, but both can lead to ketones through different reaction pathways.
It's like having multiple recipes for the same delicious dish.
I like that analogy. And this reaction is even more interesting because it involves a special intermediate called an enol.
An enol. What's that?
It's a molecule with both a double bond and an alcohol group. But enols aren't very stable and quickly rearrange to form ketones.
So it's like a quick costume change from enol to ketone. And this happens because the ketone is more stable.
You got it.
Okay, makes sense. The molecule wants to be in its happy place, the more stable form. So what else is special about alkenes? Anything surprising?
Well, this might surprise you. Terminal alkanes are actually a bit acidic.
Wait, what? Acidic? I thought hydrocarbons were neutral. Like they don't have those sour, corrosive properties that I associate with acids.
I know, it seems strange. But terminal alkenes, the ones with a triple bond at the end of the chain, can actually lose a proton.
Lose a proton. So they can act like an acid, donating a proton to a base.
Exactly. It has to do with the hybridization of the carbon in the triple bond. That carbon pulls electron density away from the hydrogen, making it easier to remove.
So that hydrogen's feeling a bit vulnerable, hanging out there on the end of the chain with its electron being tugged on.
You could say that.
Yeah.
And that makes it acidic enough to react with a strong base.
Okay, so alkenes have this hidden acidic side. Pretty cool. What else can these triple bonded wonders do?
Well, remember how we talked about alkenes forming polymers?
Yeah, those amazing long chains of repeating units like polyethylene and polypropylene.
Right. Well, guess what? Alkenes can polymerize too.
Whoa, so we can make polymers from alkenes. What kind of cool stuff can we make with this?
Lots of interesting materials. One example is polyacetylene, which is made from ethane.
Polyacetylene. That sounds pretty high-tech.
It is. And here's the really cool part. Polyacetylene can conduct electricity.
Wait, what? A polymer made from a hydrocarbon can conduct electricity. That's insane.
It is pretty amazing. This property has opened up a whole new area of research into using polyacetylene in electronics and solar energy application.
So we're talking about materials that could revolutionize our technology, all starting from those triple bonded alkynes.
Exactly. And speaking of connections, remember that reaction we talked about earlier where we pass ethylene through a hot iron tube?
Yeah, the one where 3 ethane molecules join together to form benzene.
Right. That reaction shows us how we can transform aliphatic hydrocarbons, like alkynes, into cyclic aromatic hydrocarbons.
So we're basically bending those linear molecules into rings to create those special aromatic compounds. It's like molecular origami.
I love that. And this connection between alkynes and aromatic compounds is a key concept in organic chemistry.
Okay, I'm definitely seeing how all these different types of hydrocarbons are related. It's like a giant interconnected web of molecules and reactions.
It is. And speaking of aromatic compounds, are you ready to dive into the world of benzene?
Absolutely. Benzene is the rock star of aromatic compounds. Let's hear what makes it so special.
Benzene is like the celebrity of the aromatic world. Everyone knows its structure. That 6-membered ring with alternating single and double bonds.
Right, the classic hexagon. I remember drawing those in chemistry class. But those bonds aren't actually fixed, are they?
Nope, not at all. The electrons are delocalized, meaning they're spread out over the whole ring.
Ah, so those electrons aren't stuck between two atoms. They're kind of roaming around the entire ring.
Exactly. And that's what gives benzene its special stability and makes it aromatic.
Aromatic. So it's not just about a nice smell. It's about those delocalized electrons creating that super stable structure.
But wait, isn't benzene also pretty toxic?
It is, yeah. Benzene can be harmful because it can mess with how our cells function, especially the ones that make blood cells. So it's like a double-edged sword. Stable and useful in a lot of ways, but also potentially dangerous.
Exactly. That's why it's so important to handle it carefully and understand both its chemical and biological properties.
Absolutely. Chemistry is cool,
Yeah.
but safety first. Okay, so back to those chemical properties. If benzene is so stable, does that mean it's like totally unreactive?
Not quite. It's reactive, but it likes to react in a way that keeps that aromatic stability.
Ah, so no messing with those delocalized electrons.
Right. Instead of addition reactions, which would break those double bonds, benzene prefers substitution reactions.
Substitution. So swapping out something on the ring for something else.
You got it. One of the hydrogens gets replaced with another atom or group.
Clever. That way the ring stays intact and those delocalized electrons can keep on dancing.
Exactly. And one of the most common types is electrophilic aromatic substitution.
Electrophilic, so something that's attracted to electrons.
Yep. An electrophile attacks the ring and replaces one of the hydrogens.
And what kind of things can we add to benzene this way?
Oh, lots of things. Nitro groups, halogens, sulfonic acid groups, even alkyl or acyl groups, which are carbon chains.
So we can stick all sorts of stuff on that benzene ring.
We can. And those substituted benzenes are used in a ton of different things. Solvents, dyes, even explosives.
Explosives from benzene. That's a bit scary.
Some of them, yeah. But many substituted benzenes are actually used in pharmaceuticals, plastics, all sorts of everyday products.
It's incredible how versatile it is just by adding different things to that basic ring structure.
It is. And by understanding how those substituents affect the ring's reactivity, we can control how and where those new groups get added.
Control is good. I remember learning about how certain groups on the ring can direct incoming groups to specific positions. It's like those substituents are playing traffic cop on the benzene ring.
That's a great way to think about it. We call those directing effects.
And are those directing effects related to those electron donating and electron withdrawing groups we talked about earlier?
Exactly. Electron donating groups make the ring more reactive and direct those incoming groups to the ortho and para positions.
Ortho and para.
Yeah.
Those are the spots right next to and directly across from the original group, right?
Right. It's like they're pushing extra electron density to those spots, making them more attractive to electrophiles.
Makes sense.
Yeah.
And what about electron withdrawing groups? They're the party poopers, right?
Kind of. They make the ring less reactive and usually direct the incoming group to the meta position, which is 2 spots away.
Ah, so it's all about how those substituents mess with the electron density in the ring, like a molecular tug of war. And the outcome of that tug of war determines where the new group will go.
You got it. And this concept is super important in organic synthesis. It lets us control exactly what kind of molecule we're building, adding those new groups in just the right places.
Wow, that's pretty powerful. It's like we're playing a molecular game of chess, carefully planning our moves to build the perfect molecule. I love that analogy. It really captures the essence of organic synthesis. This deep dive into the world of hydrocarbons has been amazing. I feel like I've gone from hydrocarbon zero to hydrocarbon hero.
I'm glad to hear it. It's such a fascinating field, and we've only just scratched the surface.
For our listeners who are as hooked on hydrocarbons as I am, what are some good resources for learning more?
Oh, there are tons of great books and websites out there. A simple online search for organic chemistry will give you a great starting point.
And don't forget about your local library. They're treasure troves of knowledge.
Absolutely.
Well, that wraps up our deep dive into the world of hydrocarbons. Hopefully you all learned something new and maybe even discovered a newfound appreciation for these amazing molecules that are all around us.
It's been a pleasure exploring this fascinating world with you.
And to all our listeners, keep those brains buzzing, keep those questions coming, and until next time, happy chemistrying.